right, ladies and gentlemen, we are starting a new section today. We are moving on to section 6-7. We are looking at roots and zeros of polynomials. We're going to find techniques to determine how many roots, how many zeros, what types of roots and zeros, as well as determine the factors and intercepts. All right, since factors are a product, and the only way a product can equal is if one or more factors are zero. The only way the polynomial can equal 0 is if one or more factors are 0. Okay, there are several ways we can solve a polynomial equation. One way is to rearrange the terms to have 0 on one side. The other way is to factor. When we factor them, we set our factors equal to 0. So on that screen is an example. It's x squared plus 2x equals 15. So in that space, you have space to write out the example. So the first thing you're going to do is set that example equal to 0. Then you're going to factor. So like I typed 1, 2, 3, and then you guys have to write down the work for the example. So the only two values for x that will make that equation equal 0 are -5 and +3. A polynomial function is usually written in function notation or in terms of x and y. The zeros of a polynomial function are the solutions to the equation you get when you set the polynomial equal to 0. The zeros of a polynomial function are the solutions to the equation you get when you set the polynomial equal to 0. So we previously looked at the example of x squared plus 2x minus 15. The graph of that example is on the right-hand side of your page. The zero solutions or roots are these points here, where the graph crosses the x-axis. We refer to those points as the x-intercepts. We can also refer to them as the zeros, but oftentimes you'll hear them called the x-intercepts. So point where y equals 0 is called the x-intercepts of the graph. The x-intercepts for our graph are the points -5, 0, and 3, 0. When the factors of a polynomial expression are set equal to 0, we get the solutions, or the roots of the polynomial expression. The solutions or roots of the polynomial expression are the x-coordinates for the polynomial graph. So in this unit, we've continued to look at graphing. We've looked at the zeros, the roots, and the solutions. And we're going to continue that study as we look at determining how many and what type, as well as real versus non-real. So up to this point, all of the polynomial function roots we've been finding have been real. We're now going to expand that idea into the non-real. It's also important to be able to understand terminology. So when we say polynomial function, you're talking about the equation. When we say factors, we're talking about the binomial representations of the factors. So yesterday we worked on factoring polynomials. When we talk about the roots or solutions, we're talking about x-equal values. And if you talk about the zeros or the x-intercepts, then we're talking about coordinate points. So the difference is how you are writing them. Factors have parentheses, solutions are equal, and then intercepts and zeros are coordinate points. There are polynomials in which they have a degree higher than the number of real zeros. We call those solutions the complex numbers. So when a polynomial of form p of x equals 0 of degree n, and there are only so many n roots in the real system, then that tells us that we also have complex roots. Complex roots must come in pairs. So imaginary solutions or imaginary roots must come in pairs. So what does that mean? It means if a polynomial has an n complex root, then it will have a graph with n x-intercepts. So here this graph has a cubic power, and it has 3 zeros. Therefore, it has no imaginary roots. Now, if that was to a power higher than 3, then it would have imaginary. So in this example, the degree is 3. If you factored that polynomial, you'd get the roots -2, 0, and 2. If you were to factor it, hopefully you would immediately recognize the x GCF, turning it into a difference of squares, and that's where you would get x, x plus 2, x minus 2. So what we're getting at today is that not all real roots are there. So here we have a similar degree. It is a cubic function, but now when I look at the cubic function, it only has one real zero, which means that it has two imaginary. So what we're going to work through in lesson 6-7 is to find those imaginary zeros. So we have one real at x equals -1. The other two are imaginary. So two graphs, same power, but two different types of solutions. One has one real and two imaginary. The other had three real. Now a cubic can never have all imaginary. A cubic must cross at least once. A cubic must cross at least once. Okay, so in example number 1, what we're going to do is factor that example to determine the numbers and types of solutions. So you get 0 equals x plus 3 times quantity x plus 3. So what that tells me is that x equals -3 is what we call a repeated root. That also tells me that my vertex is on the x-axis. So if I were to graph this function, I would know that the x-axis or the x-intercept only crosses once at -3. My parabola is going to open up and have no other real zeros. So it says determine the number and type. So we have two reals. So the number is 2. The type is reals. Example number 2. We have 0 equals x cubed plus 25x. So the first thing I'm going to do is take out my GCF. So that leaves me x squared plus 25. So then we're going to set each factor equal to 0. And I get one real root off the bat at x equals 0. And then by the zero product property, we set x squared plus 25 equal to 0. And then upon doing so, you get x squared equals -25 because we subtracted to the other side. To get rid of something squared, you square root it. And when you square root a number, it gets a plus or a minus. We previously learned in chapter 5, if you take the square root of a negative, it gets an I. The square root of 25 is 5. So we get x equals plus or minus 5i. The minute an answer has an I, it tells me it's imaginary. The plus or minus gives that pairs of imaginary. So this is a degree 3 making it a cubic. So again, if you're classifying this, it's a cubic binomial. And it has 3 roots, where 1 root is real and 2 are imaginary. So that means if you were to graph this, the graph would go through 0, 0. It's a positive cubic, so that means it starts low and goes high. And somewhere in there, we also have another set of bumps to represent that plus or minus 5i. Okay, in example number 3, we have x to the 4th minus 16. So this is kind of like our cubic technique, where we would say, or not cubic, quadratic technique, where we would say that u is equal to x squared. So this becomes u squared minus 16. Which makes it a difference of squares, which means that it factors as u minus 4, u plus 4, and then we replace our u back with x squared, and then this is actually another difference of squares. And now we're in factored form, so you're going to set each root equal to 0. So I get x equals 2, x equals negative 2. So those both represent real solutions, and there are 2 of them. Over here, I have x squared equal to a negative. The minute I have a square equal to a negative, I know that that's going to give me an imaginary. So I get x equals plus or minus 2i. So that represents 2 imaginary solutions. So again, my original power is 4. So if I have a degree of 4, then I need to have 4 types of roots. And in this case, I have 2 real and 2 imaginary. So I also have the answer keys to homework that you uploaded for me today. I'm going to post those pictures on our Teams page so you can actually check your answers to that packet. And then I'm going to give you some time to work on 17 to 26 and ask any questions you might have had on the previous 6-6 assignments.